All right, so we're just going to formally discuss what we had kind of covered when we talked about transformations. It's just we're going to sort of go back and really kind of delve into it a little bit more. Thumbs up, nice. I like it, a thumbs up. I also like nice messages on my YouTube channel. That was a good one. And obviously thumbs up on my YouTube channels. That has not been happening as frequently as I thought it would have been, but it's all right. I don't have to be in a good mood when I'm putting together the next unit test. Thumbs up, it makes me smile. You know, each one. 10 questions on the next test. Maybe 10 thumbs up for each of you, and off we go. I don't know. We'll see. So anyway, vectors in space are written with the three components: v1, v2, v3, a, b, c, whatever, something else. Right? Just three components, three non-necessarily numerical components, but those non-numerical components would represent something numerical, so they're constant values. The standard unit vectors in three dimensions: 1, 0, 0, 0, 1, 0, and 0, 0, 1. We focused on 2 dimensions, so the I and J in 2 dimensions was 1, 0, 0, 1, and so that's where we came up with our standard identity matrix in 2 dimensions, which is 1, 0, 0, 1. It was just based off of these 2 components. But now we're going to have a 3 by 3 matrix that represents the identity matrix, also based off standard units. But specifically, we think of these as the basis vectors for 3 dimensions. All right. So what does that mean? That means that you can represent everything else based off of these 3 standard vectors. So if we want to write a vector, some vector v, where's that string off there? I think that might just be schmutz. Oh, it looks nice around here. It's the actual arrow, but it looks like schmutz on here. But, yeah, whatever. We can write it in IJK notation. It's sometimes more convenient because we're thinking of it as a linear combination. Right? So writing it in this form just makes it easier to perform any operations. All right. So our rules, we have our scalar multiplication, we have our vector addition, which we know about, and we also know how that manifests itself graphically, or at least some of us do. Oh, that was not. So, but I am going to, I think, go over that. Just, you know, let's go over that right now. So, vector addition, for example, let's say you had 1, 1, 1 plus, I want to keep it simple because I don't want to create anything too crazy. 1, 0, 1, 1. It might overlap too much. Let me get some negatives in there. Like 1, negative 2, 2. All right, the addition of that is very simple. Right? You just add them together. When I ask for a graphical representation, when I say to graphically find the sum, I don't mean, and we talked about this in class, and in fact somebody asked the question. It was a good question. So could we just add the 2 vectors and then plot that? Well, that's not graphically finding the sum. Graphically finding the sum is plotting the 2 vectors here's my 1, 1, 1. 1, negative 2. So 2 would be, so something like, let me just do this in red. Okay, so those are my 2 vectors, the 2 that I need to find the sum of. To graphically find the sum, and I know the one on the test is a little bit more complicated, but you know, with an index card and a little bit of patience and giving yourself a little bit of room, you get it done. You're going to create a parallelogram out of this and then plot the diagonals. So you're looking at all right, so if I'm calling this U and I'm calling this V, that this blue vector here would be U plus V. Okay, so that was the way you should have done it. You did it any other way, you know. I'll just put it this way. If it looked like you were just trying to manufacture what you got when you just added the 2 vectors together, being like, all right, I know it's supposed to get to 2, -1, 3, so let me just draw some arrows that get you there, and you didn't get much credit for that, right? So yeah, you kind of want to start thinking about the difference between the way you might have learned something previously and the way I'm asking you to do something, because on a test, I'm asking you to do a particular way, so just be mindful of that. There are some exceptions to that, and we've talked about it as we've gone through the content. If you've asked during class, hey, can we do it this way? And I say, yeah, then you can do it that way. But if I say, like in this instance, if I say, I want a graphic solution to look like this, then it should look like this. All right, vector magnitude. Well, in 2 dimensions, it's a little bit simpler, but it's a Pythagorean relationship. Right? In 2 dimensions, you're basically looking for the hypotenuse of the triangle that's created by the vector. So if you create a vector that's going off into space in 2 dimensions, find the 2 legs, use the Pythagorean theorem to find the length of the hypotenuse, and that is your magnitude. You don't really need a rule for that. But in 3 dimensions, I guess you really still don't need a rule for it, because if you realize that everything just kind of expands to an additional dimension, then you would see that this is Pythagorean, but in a 3rd dimension. Now, maybe the justification of it would be something that's a little bit more elusive at this stage of the game, but that's a little bit more Calc 3-ish, I guess, or at least it's explicitly stated in that curriculum that it's covered there. Here we just kind of use it, because all I need to do, and I can go over the derivation of this at some point, but just bear in mind, if I take the time to do that, then it could work its way onto a test. And, but if you're really interested in it, and you really don't want it to be on the test, but you really would like to learn it, then that's one of those see me after class kind of things, because you don't want to get the death stare from 23 other people in the class when you realize that you just put them on the hook for something that only you were interested in. All right. Now, if I get 24 emails after class saying, hey, I'd really like to know where that came from, then that's cool. Then I will go over it in class. Either that or I'll explain 24 different times after class. Anyway, at this point, I don't think I really need to convince people that, you know, at least it feels right. It feels like a rule that probably works. Okay, so that's what we'll go with. Unit vector in the direction of V. First, we find the magnitude, and then we divide each of the vectors by the magnitude of that given vector. What that does is it creates a new vector whose magnitude is equal to 1. All right, so that's the definition of a unit vector. For that, I can do a quick example. Something not too crazy. I'll take my V from earlier. 1, -2, 2. One, because it's not too difficult to compute. Also, it's what I called vector v earlier, so why not? All right, so I'm going to find the magnitude of that. So this is v. So the magnitude of v, square root of the squared components. So 3. 4 plus 4 is 8, plus 1 is 9. Yeah, 3. Oh, that's exciting. Just made up one off the top of my head and it ended up being nice. All right, so that's the magnitude. So that in fact is the length of the line. It goes as an absolute measure. Right? Alternative way of representing the magnitude is with a single absolute value bracket. I just like the way it looks with the double. So you can go either way on that, so you wouldn't get in trouble if you went either way. But one of the benefits of using the absolute value symbol is that it becomes obvious that you're looking at something that should be a positive quantity. Okay. Anyway, so if I want my unit vector in the direction of v, it would be each one of the components of that original vector divided by the magnitude. So 1 over 3, negative 2 over 3, and 2 over 3. So I won't bore you with the details here, but if you were to then find the magnitude of this, it would be equal to 1. Actually, it's not really difficult, I guess, because square each of these components. 1/9, 4/9, 4/9. So 9/9, 1, square root of 1 is 1. All right, so, but you can, if you want to do it out by hand, those are the details I won't bore you with. All right, so not too bad. What it allows us to do moving forward is establish characteristics of a particular vector to be the basis of other vectors. All right, so we would create transformations that would allow, if I wanted to redefine my number system to be based off of this vector 1, -2, 2, having that unit vector would go a long way to make a determination of what the basis of that numerical system would be. So I can create a system that would be multiples. We would be counting in terms of vector v, the unit vector v. So there's more to it than that, but that's kind of where it all starts. All right. The example here just kind of rehashes pretty much what I just did, so I don't think I need to do anything but put a nice star on that bad boy with my creative pen.